So happy Friday, everyone. Does anyone have any questions before we start? No questions? No questions is good news. It means everybody's happy, everybody's satisfied. Everybody knows the answers. Okay, good. I have a question for you guys. Does anybody remember where we left off? So let me see if I can figure that out. So we started to talk about subsystems last time. And this is near the ending stages of our design process, our object-oriented design process. And we talked about collaboration graphs for subsystems, and we talked about visual representations, especially this nested representation. And you might remember I said I thought it was confusing because the hierarchical and nested representations are combined into the same diagram sometimes, or oftentimes. We talked about this confusing multiple inheritance example, how to represent contracts visually, how to define subsystems, how to define subsystem contracts, and that is possible to, instead of a bottom-up approach where we collect classes and objects together, we can do a top-down approach, which is taking a big system and then subdividing it recursively over and over again until we get to the individual object level. And then we talked about how to document subsystems, how they're actually documented on paper, and some guidelines to identifying subsystems, and then what is an example subsystem card, and then example subsystem graph. This is the notation that's used in the book that we're drawing the material off of. That's the same one in UML. And I think this is where we left off. Anybody have any comments? Does anybody else think this is where we left off? Or am I the only one? Everyone was asleep last time. I think this is where we left off. So if there are no objections, we'll continue from here. This is just another example of a subsystem. The rest of this part is just some examples of subsystems, that's all. And in many ways, the design patterns that we're going to talk about next week are all different kinds of subsystems in many ways. So they're very similar examples in some ways. An editing subsystem, this is from that reoccurring application that we're always talking about, the drawing editor that lets you draw figures. We're going to keep using that example, by the way, like the visual paradigm. So this subsystem handles user interaction for editing a drawing, right? And it has two contracts. So instead of collaborating directly with the drawing editor class, we've defined a subsystem called the editing subsystem, and we collaborate with the editing subsystem. And the advantage that offers is we can add new classes inside the editing subsystem without affecting the classes outside, because we're communicating through this subsystem interface, right? The internals can change without affecting the the external system, right? We have a drawing editor class, a tool, parent class, and then a subclass called selection tool or creation tool. Here's that same subsystem drawn in UML notation. It's a little bit more, I don't know, you could say user-friendly because instead of numbers, there are phrases here. But the part I find confusing is that we have this kind of collaboration, these collaboration edges, and then we have these hierarchical edges mixed together in the same diagram. I personally find that confusing Maybe nobody else does, maybe it's only me. And here is another example of an application from kind of a top-down perspective defined as subsystems. And this is the GUI subsystem, so it handles all the user input. Here's another system called the editing subsystem, where you're actually clicking on different shapes and changing the location of the vertices. And then there's the canvas where everything appears. This might look familiar to some people. It's kind of it overlaps with a design pattern. I don't know if anybody has looked into design patterns yet. Has anybody looked into design patterns yet? One person. What's your name? Shelsky. Shelsky. Did you look at the lectures from last time, at the design pattern lectures?
I was looking for it on my own, so.
Does this remind you of anything?
I don't know, maybe the observer concept.
It reminds me of the MVC pattern, where the GUI application is the controller for the user input, and then the editing subsystem and the drawing subsystem are the view part of the MVC pattern. This is that same one in the UML notation. That would be a great test question, by the way. Like, take these subsystems and convert them into the MVC design pattern. That would be a great test question. Okay, so one of the whole ideas behind subsystems is to simplify the interactions so that every class does not interact with every other class. That's the kind of system we're trying to avoid. Complex interactions are hard to maintain and lead to so-called spaghetti code. I think it was Benjamin that mentioned spaghetti code. Is that true? Is my memory? If he's here today. Complex interactions are hard to maintain. Simplifying interactions simplifies the collaboration graph. Areas of complexity in the graph can be the focus of the simplification effort. Guidelines for simplifying collaboration patterns. Those are some advanced guidelines there. Minimize collaborations of a class with other classes and subsystems. Minimize the number of classes to which a subsystem delegates. And minimize the number of different contracts supported by a class or subsystem. So the introduction of subsystems itself is a way of simplifying interactions in the system. That's one of the main objectives of subsystems. A design is simpler with fewer collaborations. So if we can reduce collaborations, we should eventually, if we can. We might be able to reassign responsibilities from inside of a class to a subsystem. There has to be some collaboration between classes and subsystem interfaces. And one approach is to centralize the communications flowing into subsystems. That's the whole idea. So create a subsystem interface class that helps to hide the details of what's going on inside the subsystem from what's taking place outside the subsystem. And I believe we have some examples of that. So this is the print subsystem again. So the idea behind the print subsystem is to hide the details of specific printers from a user. Like here at university, you can print things, right? And anybody notice that the printers are old? They're kind of old. Don't they seem really old, the ones at in the computer science building? So I hope they get upgraded at some point, but when they do get upgraded, we shouldn't have to change the way we print, right? With the complexity, if one printer gets swapped out for another one, we don't want to have to then change the way we print. We still want to hit the file menu and then the print command, and hopefully it still works, right? If the software is designed really well, then that change will be quite easy. So print a file, send a file to the printer, associate it with a form, and notify the operator to load a form, for example. Right? And this is the visual representation of that interaction. And we should be able to swap out the printers, the old ones with the new ones, without actually affecting the user. The user should not have to worry, if you come in one day and there are new printers, it shouldn't cause a big problem, right? So by minimizing the number of classes that receive a subsystem contract delegation directly, you hide more of the subsystem and get better encapsulation. And yes, we're going to see some visual representations of this idea. Here's another example. This is from kind of a retail example, retail sales, right? Imagine we have some sort of a retail environment where we're trying to sell things. We have a cash register. Does everybody know what a cash register is? Here it's not called a cash register, right? Does anybody use the phrase cash register here? One person? I can see everybody was out partying last night. Happy Halloween. Till, right? You use the phrase till in the UK. This is the till. You have a warehouse class, and then you have this subsystem for trying to keep track of the inventory, right? What have you sold? What have you not sold? When was the item sold? How much did it cost? And all those details in this subsystem. So this is one way to kind of represent that visually, like the cash register interfaces with the inventory subsystem, and the cash register interfaces with the transaction log and also the accounting system, right? Maybe it subtracts, it tells the inventory class -1, we just sold something, so lower the numbers down. And then the next one is, okay, this is the time at which this item was sold is recorded, and which item it was, what the SKU number is, and so on. And then we have the costs, like how much money did we just earn. But that's a complex set of interactions, right? So we could modify that subsystem to simplify the pattern of communication. And the idea is to introduce another class called the inventory manager, right? That's one subsystem interface class, and all the communication goes through that subsystem interface class. So the cash register only has to know about one interface, and that is the inventory manager, and then all this other complexity is hidden. Right, and we can swap out the transaction log. Maybe the transaction log used to be stored on Microsoft clouds, and then we changed our mind because they got too expensive, and now we're storing the transaction log on the Amazon cloud services, for example. And we should be able to make that swap without destroying everything, right? Make it invisible to the person at the cash register. And here's another example of that visually. Here's a subsystem with 1, 2, 3, 4, 5, 6 contracts being redesigned into two contracts with the subsystem, and then the other contracts are delegated to classes inside the subsystem. So it makes the pattern of communication simpler, right? The outside view of that system is much simpler now. Okay, so after we've introduced subsystems into our design, we have to then factor these into the rest of the documentation. We may have to redefine contracts. Contracts that used to belong to individual classes might get moved to subsystem classes or subsystem interfaces. We might have to revisit the collaborations, right, to incorporate the new subsystems. We may have introduced new classes, especially the interface classes for subsystems. So we may have to redraw a lot of our original drawings, right? The hierarchy graphs might change, collaboration graphs will change, and we'll have to kind of start from the beginning and update all of our documents and documentation in our design to incorporate these new subsystems that we introduced. Okay, any questions about subsystems? Good, good, very good. So we'll finish the topic of subsystems then, and we'll move on to Is it working? The problem of presentations is still unsolved. Any questions before we start protocols? So what we just talked about over the last 2 weeks was how to go from a specification to a design, right? Where you learn how to define objects, you learn how to define responsibilities, you learn how to represent the patterns of communication between classes and objects. We learned how to introduce subsystems into that design. And now we're going, what is it doing now? During a presentation, asking for feedback. Now we're making a transition. So we're doing these transitions along the software development process. We went from requirement specification to design. That's that transition we just made. And then the next step of the software development process, does anybody know what the next step of the software development process is? The classic next step? Name?
The actual coding process.
Exactly. What's your name again? Emily. Yes, somebody is awake. Emily is awake. So now, how do we transition from the design to the implementation? How can we make that transition, right? Does anybody already know the answer to that question? You'd be a powerhouse, like kind of advanced person if you knew the answer to that question. Well, the answer is actually on this slide. It's using protocols or developing protocols, which is what we're going to talk about right now. So it's the transition from design to implementation, assuming the slides work. But before we jump in to protocols, I thought it would be fun to look at this one. There are two drawings here. One is a Windows server, one drawing, and another is a Linux server, and that is the so-called map of system calls that occur when a web page is served. Right? You point at your browser at Amazon.com, and it serves up a web page. And there's some web server software that's responsible for that, and this is a map of all the system calls that occurs. So you could also call those collaboration graphs. Why is that important? This is important for security purposes, right? System calls can lead to breaches in security. The more system calls there are, the greater the potential for vulnerability, right? And more effort is needed to create secure applications. So the quiz, anybody want to know what the quiz is going to be? So the quiz is which one is the Linux server and which one is the Windows server. That's the quiz. Name?
Daniel.
Daniel.
I'm going to say the top one is Linux because it's like less messy.
Correct. Easy quiz. Easy quiz. Happy Halloween. A little bit late.
Oh, good.
Yeah, so imagine you're a new developer and you have two choices, to find a bug in the Linux server or to find a bug in the Windows server. Which job would you take? Yes, so this is why the Linux server is so popular. The Linux web server is the most popular web server. And that's because the person who worked on the Linux web server knew about software design. They knew that software can be designed before it's implemented. But the people that worked on the Windows one, not sure. Not sure if they knew that. So a protocol corresponds to the signature to which a class responds. That means the method name, the set of input parameters associated with the method, and the set of return parameters. This is the final step of the design, or you can think of it as the transition from design to implementation. So we have a set of classes, we have a set of subsystems, and for each class we now define protocols. So we're going from responsibilities that were written in natural language, and we're translating those into actual method calls. That's the transition. So from design to implementation. We have to think about getting our responsibilities more well defined, so they have to be more precise. And we have to think about the names. What kind of naming conventions we're going to use. We also have to think about input parameters. Like, for example, if you have 3 input parameters, what order should they be in? Anybody know the answer to that question already? That's a very advanced question. If that appeared on a job interview, that would be shocking. But it is a valid question, and we're going to actually address it in this lecture. Should I tell you now, or should I wait? I guess I'll wait, just to keep the suspense up. But it's some of these things are people don't think about them when they're designing their software. But they're definitely worth thinking about. We're also going to think about default values and some other things associated with protocols. So we're writing a design specification for each class and subsystem, and we're writing a design specification for each contract. So we're making this transition from natural language to actual code, right? And that's going to force us to be more precise, right? We have to, anything that might have been unclear or fuzzy before will become magically black and white. Not really, but no more hand waving anymore. I still remember learning this, by the way. I still remember sitting in your seats, learning this as a student, and watching the professor, who was my master's thesis supervisor, deliver this lecture. And I was sitting there, I remember sitting there looking, and I just thought to myself, this is never going to work. Never going to work. Because we had to then do it. We had to get organized into groups, and we were given a system specification, and then we had to produce the design and then implement it following this process. And I was wrong. I was absolutely wrong. We followed the process. We got to the protocol definitions, and we were able to join all of our pieces together very smoothly, and I was shocked that it worked. I remember going through that process. So we need to derive an implementation for our classes, right? Our classes so far, they look like a set of contracts, responsibilities. They may take on the role of clients and servers. The implementation is represented by a protocol for each contract. In other words, the method name, the set of input parameters, and the return parameters. And maybe some protocols for private responsibilities, but we're not going to focus on the private responsibilities. We're going to focus on the public responsibilities. And one general guideline is to avoid specifying the implementation details, right? We don't need to get too detailed. And we're also focusing on what the protocols are, but not how they're implemented. Like, what protocols do we need? What does this object need to do? What services does it provide? Not exactly how, right? Because there are an infinite number of choices for how a responsibility is implemented. Okay, method names. This is something that not many people think about very much. Well, some people do. The people that are really good at writing good code think about this stuff. But if you don't think about it, you're going to run into some big problems. So one of the ideas behind method names is to preserve encapsulation and information hiding. The careful selection of method names is critical for reducing the design complexity, right? You've already heard these terms, overloading, right? Proper overloading can be an important vehicle, but it can be confusing if a name is used for two conceptually different things. It can also be confusing if two different names are used for the same conceptual responsibility or the same action. So the choice of a method name is as important as the choice of class names. Each method name should imply a unique intent. There should also be something here about a verb, right? Each method name is a verb, right, as opposed to a noun, generally speaking. Use the same name everywhere for each conceptual operation, and associate a single conceptual operation with each method name. And classes that fulfill the same responsibility should inherit it. In other words, they should share the responsibility through a parent-child relationship. And we'll go through some examples here. The drawing editor example that we've come to know and love. We have a class called drawing. We have another class called drawing element in our example. Both respond to a display message or method, you can think of it. Although the implementations are probably different, it's the same conceptual operation. For example, a drawing knows how to display itself, and a drawing element knows how to display itself. So they're both going to have a method inside of them called display that are conceptually the same, but maybe the implementation is different. Well, yes, the implementation is going to be different. Can anybody think of a very common example in Java of this same idea? There's a very ubiquitous example in Java that is using the same idea, the same conceptual operation, but with many, many different implementations. And I think it's in there is like the Java object at the top of the Java hierarchy, right? Everything inherits from Java object, and it has a responsibility that's very ubiquitous. Is it Emily? What? Yes! Oh my gosh! It's the toString method. Every method has the toString, right? It's conceptually the same thing. but the implementation is by definition different for every class because every class has a different name, right? You can always do like printf, you know, whatever that Java class is. Printf is not Java, is it? I think that's C++, but you know what I mean. Yeah. So same idea. And by the way, when you look at the Java API, it's following all these rules. So if you're ever wondering or looking for examples, they're all in the Java API. It follows all these rules beautifully, actually. Okay, so we could introduce an abstract class called drawable object from which drawing and drawing element can inherit the display responsibility. The point there is they both have that responsibility, and somehow there should be some shared behavior represented there. So here's an example of some protocols. A protocol for a contract or a set of responsibilities must cover the full generality of each responsibility in a contract. And you've seen this a lot in Java as well. Several versions of the same conceptual method. You see that a lot. But maybe they take different input parameters, or maybe they have different return parameters, depending on the variety that you're interested in. A simple responsibility may only need one signature, right? An array is responsible for knowing its size, very specific, so there's only one protocol there. Like, it could be called get size, right? Or get length or something like that. But a more general responsibility may require several signatures. So an array is responsible for enumerating over its elements. So it could have a find first protocol, for example, a find last protocol, a find all protocol, a reject or skip over elements protocol, for each perform some operation and for each undo some operation. So that's a very general set of protocols for enumerating over some elements in an array. Right, so enumerating over its elements is a responsibility expressed in natural language, and now we're going from natural language to a programming language. That's another way of thinking about it. So from design in natural language to implementation. Okay, this is one of my favorite slides, by the way. Define reasonable defaults. Defaults are huge, absolutely huge, and they don't get discussed or thought about. Why are default values so huge? Why are they so important? Anybody know the answer to that question? Anybody ever think about default values? I'm sure you all have thought about default values before, but maybe you haven't thought about them as important default values, but you've thought about them in other ways. Default values affect your lives very heavily. Does anybody know why? Name? Ollie.
Like if your parameters are missing or erroneous, then it will still work because you have a backup option.
That's right. That's a good answer. That's a good answer. Any other answers? So with good default values, your software should still work. That was like the summary, I think, of Ollie's answer. Any other thoughts on default parameters? Well, one reason they're important is because there are millions of defaults. There are millions of them. If you pay attention, they're everywhere, right? Like, what is the default background color of my slide? Or what is the default background of my phone going to look like? What is the default sound that's made when I get a message, right? The defaults are coming at you all the time. Like every 5 minutes, you're being introduced to a default value. They're incredibly important, and they have massive, massive consequences. Therefore, we want to think carefully about, because the default values have such massive consequences, we want to think carefully when we choose them. And this is something that most people don't do. They don't think carefully about their default values, and it has massive consequences. One of my favorite examples is just printing. Like when I print a file, the default value is usually one-sided paper, but actually most printers are two-sided. So somebody chose one-sided as their default printing value, and they've cost who knows how many millions of pages of paper just because somebody thought, oh, I guess I'm going to choose one-sided as my default for printing instead of two-sided. And that default value has resulted in countless, right, extra pages of paper being printed. And because there are so many default values, there are millions of them in our daily lives, we don't have time to change them all, right? We could spend all day trying to change the default values, and we do change them sometimes. We might change like 2% of them or something, right? But we don't have time to change all the default values. And so when somebody makes this decision on a default value, it actually can have massive consequences. So we want to think about good default values, generally speaking. Very, very important. So classes are more easily used and reusable if protocols are designed to reflect their different uses accurately. And we can speculate on potential future use cases to make abstractions and generalize. So always start by defining the most general message or the most general method, you could say, allowing clients to specify all parameters, provide default values for parameters as appropriate, and analyze likely uses. Determine a set of signatures that require only subsets of parameters in order to make the signature match naturally. So this guideline is kind of a paradox. Always start by defining the most general message or method, allowing clients to specify all possible parameters. Does anybody see a kind of, I don't know, it's not maybe a problem, but it's something in that guideline that's not very nice. Let's just say it's not nice. This is an advanced question, by the way. I wouldn't expect most people to know the answer to this question. What's not nice about that guideline? You just said your name. Ollie. Ollie, what do you think?
The fact that a client can specify all parameters, maybe they can have access to some of them.
So the idea that some of the parameters should be private and not public, that's not a bad answer. It's not the answer I was thinking of. But I'm sure you've all noticed that the more parameters a method takes, the more difficult it is to use. Right? If you're trying to call a method that has 10 parameters, you don't use it because it's too much work. It's like, really? I have to specify 10 parameters to this method? I'm not going to use this method. So the best methods take 0 parameters, actually. Those are the ones that we're going to use the most frequently. We like methods that require no parameters, actually. Those are the ones we want to use. Those are the easiest, user-friendly ones. So for example, the display method, coming back to the display method, the drawing editor might identify the following parameters. The device to receive the display, maybe it's a desktop, maybe it's a laptop, maybe it's a phone. a transformation from mapping each object's coordinate system to the display coordinate system, right? A phone coordinate system might be different than a desktop coordinate system. A clipping region of the display coordinate system, only elements inside this region are actually displayed. So maybe there's a bounding box that says only display the elements inside this bounding box, and a drawing rule to indicate how many images, how they're to be overlaid. In other words, the default drawing rule is usually most recent object comes on top and is drawn over the previous ones. That's the general default, which, by the way, is a huge decision. It's a huge default decision that we don't think about, but somebody has made that decision as a default, and it's huge. It has massive consequences that we are experiencing every day. So the most general signature would need to include all of these parameters, but what should the order of the parameters be, right? That was that question I asked at the beginning. Like, nobody thinks about this stuff. Nobody, but you guys are now smarter than 99% of the other software developers, because you're going to start to think about these things now, like important default values and the order in which parameters are given in the method. So the idea is to order the parameters based on the probability that they'll be used. So the most frequently used parameters come first, right? So from most popular to least popular. You might not be able to actually determine that. You might have to make some educated guesses, but that's the idea. So looking at, we want to also have reasonable default values, right? So in case we want to make a user-friendly version of this method that doesn't require all the parameters. The default display is the active window or the current window. The default background color is white. I personally get really annoyed but when somebody chooses the default background color as black. I hate that. So you might have noticed, like in IntelliJ, the default background color is black. I don't like that at all. Anybody else not like that? You get a piece of candy for that. The love hearts. Like that, you know, that black background, the default black background. I'm going off on a tangent here, but that implies, in my mind, maybe I'm crazy, but in my mind, the developer that made that decision was a night person, like the kind of person that wants to do their work and their development at night, and that's unhealthy, actually. Like, we should work during the daytime, generally speaking. Of course, there are exceptions. But it's best to work during the daytime and get some natural light, get exposure to sunlight. Sunlight is healthy. Anyways, I'm rambling a little bit. The default clipping region is the entire display. In other words, ignore the clipping region, and the default drawing rule is over. That means when you draw two items and they overlap, the one that's drawn the most recently appears on top. That's what that default rule means. Usually we don't like to have overlap, but so in this example, display and region are the most likely to be specified, and the transformation is the least likely. So this is not the world's most black and white example. So here's a set of protocols or signatures that we can add into our implementation. So we support the display method with no parameters. That's the one everybody's going to use, right? It uses all the default values, and then we add other options like the device option, the clip region option, the device and clip region options, and then so on. And then here's all 4. And you see this, and if you look at the Java API, you see this kind of thing all the time, right? The same method name, but with different input parameter options. And these are more options that are possible. Any questions so far about protocols going from design to implementation?
Yes, sorry, can you go back to the previous slide?
This one? Mm-hmm.
So, can we define method with the same name but with different amount of parameters in Java? Is that possible?
Yes, it is possible. You see that many times actually. Yes, if you look at the Java API. Ready? So he said, can you specify a method name, or several versions of a method, but with different input parameters? Yes, you can. And it's very common actually. And not only that, it's encouraged. The implied message here is you are encouraged to do this. Have a method with the same conceptual responsibility. Like, for example, the conceptual responsibility of the display method here is always the same. Show yourself, display yourself. But the implementation is varying, right? And the input parameters are changing sometimes. By the way, this is the version that everybody will use, right? Because it's easiest. And then how would we actually specify those other parameters in a kind of user-friendly way? Did you just wake up? How would you specify the other parameters in like the kind of in the more developer-friendly way? Were you going to answer the question, or were you just yawning?
No, it fell out my head.
I see. Okay, I got the candy anyway. You ready?
Oh, yeah, go
Kids, are you awake enough to catch this? Oh, close. My bad. So nobody wants to answer that question? It's not a very difficult one. Name? Hawkeye. Symbolic constants. That's not exactly the answer I was thinking of. Any other name? Data types. That's also not the answer I was thinking of. But anyways, I still have leftover Halloween candy. I'm never going to get rid of. This is an easy question actually. It's getters and setters, accessor methods, right? You're going to change the device by calling set device or get device. And you're going to specify the clip region with a set clip region method or get clip region. Say that 10 times fast. Okay, I think we're almost finished, but we're not exactly finished. But the time is up. So we'll stop here. Any questions before we all run away and start drinking? Okay, let's stop here. It's the time to stop, right? Yes, it is. Enjoy your weekend, everyone.